Hello, I'm Lou Bloomfield and this is How Things Work. Today's topic, bicycles. Bicycles do something remarkable. They stay upright easily despite having only two wheels, only two contact points with the ground. Most things that touch the ground only at two places tip over easily and often. So why is it that a bicycle stays upright? And why do we ride two-wheeled vehicles around town? To begin to understand that problem, I'm going to take a step to the side and look at three-wheeled vehicles or maybe four-wheeled vehicles, things like tricycles or wagons or cars. Why are those three or more wheeled vehicles stable when a bicycle's not? And we'll look at why the bicycle's not in a moment. So with a tricycle, when you plant a tricycle on the ground, it makes contact at 3 points on the ground, and it defines a polygon, a triangle actually. This is not a tricycle, this is being a box. It's got 4 contact points with the ground approximately, but you can see, I'm going to do it like this. It's touching the ground at 1, 2, 3, 4 points, and maybe in the middle, but we can ignore those. If I hollowed it out, it would really only touch at 4 points. And that allows it to be wonderfully stable when it's sitting still. If I tip it away from perfectly upright, it spontaneously goes back. It likes to be stable here. It rocks a little bit there, but it's settling down as it was. Well, the recipe for how to make a situation like this that is stable is that those contact points with the ground define a base of support. So in this case, it's a square. Well, that's not even a square, it's a rectangle. That point, that point, that point, and that point, they define a rectangle on the ground. And as long as the center of gravity of this object, this box, is vertically above that rectangle somewhere, it's stable. It will not tip over from this point. And furthermore, if you take it away from this point, it will spontaneously go back. Well, at present, it's actually in an equilibrium. The net force on it is 0. That's what equilibrium in this context means. And it's motionless and staying motionless because it's not accelerating anywhere. If I tip it away from equilibrium, restoring influences appear that push it back toward equilibrium. So this equilibrium has a special character that wherever I take the box away from equilibrium, as long as I'm reasonable about it. If I take it too far, I'm in trouble. But a little bit away, it spontaneously goes back. It's pushed back or twisted back or a combination of the two. So this kind of equilibrium is known as a stable equilibrium. A stable equilibrium is one that when you're in the equilibrium, of course, you're experiencing zero net force, zero net torque. You can be motionless there and stay motionless, no accelerations. So it's equilibrium, and the stability means that when you depart from equilibrium a little bit, restoring influences show up, ones that push you back towards the equilibrium, like this. And this is experienced. Was that a force or a torque or some combination of two? It's a mix, and it restores the box to equilibrium. It's stable. I gave you the recipe for that, and actually just the general recipe. The physics isn't in this yet. It's just how do you set it up? Whenever you have something touching a surface, sitting on a surface, if it defines a base of support, so this one defines a rectangular base of support, a tricycle would define a triangular base of support, a cylinder would define a base of support that is itself a circle. As long as the center of gravity of the object sits somewhere above that base of support, it can be in a stable equilibrium. So in this case, the center of gravity of the box is somewhere dead center in the middle of the box. I can't touch it. The box has some thickness, so it's somewhere in there. I can't get at it, but it is above that rectangle down there. Got it? That's the recipe version. What's the physics underlying that? Well, the physics underlying that is that based on geometry, once you've got that arrangement where the center of gravity of the object is vertically above the base of support, any tip that you make in the object will raise the center of gravity upward. So the effective location of the object's weight will move upward. It's just a geometry problem. You can sort of see it here. If I tip this guy, my finger, which I'm touching here, moves a little bit upward. As a result, the gravitational potential energy of the object, in this case the box, increases. So this arrangement is actually the lowest accessible gravitational potential energy for the box, as long as this doesn't tip too far. I mean, I can do this, of course, but that's not what we're talking about. Little tips will increase the gravitational potential energy. And that gravitational potential energy is pretty much the only potential energy the box has worth paying any attention to. No elastic potential energy, no nuclear potential energy that we care about, no electromagnetic potential energies. It's gravitational only. So this orientation, like this, the equilibrium, is the lowest total potential energy that box can have. If we tip it, the potential energy goes up. So, according to the rule that objects accelerate in the direction that reduce their total potential energies as quickly as possible, this box, once you've tipped it and let go, it accelerates back towards the equilibrium to reduce its total potential energy as quickly as possible. That's what makes this a stable equilibrium. It's a minimum, I mean, a physicist or a mathematician would say it's a minimum of total potential energy, at least given that we're not going to take it too far away from this point. If we really take it far away, we can find even lower values of total potential energy. But it's the local minimum is what a physicist would call it. And local minima in total potential energy, right there at the bottom of that possibilities, those are stable equilibria. They show up all over the place. A ball rolling in a curved bowl. It'll roll around, always trying to settle right in the bottom of the bowl where it is as low as possible and has as little total potential energy as it can come up with locally. Again, you can take the ball and drop it off into a well somewhere, but that's not the story here. We're just staying within the bowl. That's the lowest place it can be. And it will go there, tend to settle there, and then be in a stable equilibrium. If you disturb it a little bit, it goes back. So returning to a tricycle. When a child is sitting on a tricycle and not waving themselves around in all kinds of crazy places, that tricycle forms a triangular base of support, and as long as the child and tricycle's combined center of gravity is above that triangle, they can be in a stable equilibrium. To be in it, they've got to get the kid to stop moving, just be still, have all three wheels on the ground, let things settle, then they're in the stable equilibrium and they're free of torques and forces, and furthermore they're motionless, so they stay motionless. If the child tips themselves far off to one side or the other, it is possible to take the center of gravity somewhere so that it's no longer above the base of support, in which case there is now a direction in which they can tilt such that they will reduce the total potential energy, and they'll tip over. So that's really what's happening. I guess I can illustrate that. I've got a stool here. It's got 4 contact points with the ground. I could do it with myself on it, but let me do it without me on it. This has got four contact points with the ground. It truly defines a nice square base of support, and the center of gravity is probably right around here, given there's a lot of weight in that top. If I started putting stuff over here that dangled off to the side, we could get this whole thing to tip over. Can I do that? Usual thing, I'll plan ahead. I can do it by I can also show you, I can take it too far off to one side. If I take it too far off to one side, so the center of gravity, which is about here again, is now outside even the edge of what used to be the base of support. Now, of course, if I let go, it tips over. It now has a direction it can tip in that instead of raising the center of gravity, it will now lower that center of gravity. It's getting lower, and it will accelerate in that direction, and we will not go back to the equilibrium. But as long as I don't tip it very far, nice, stable equilibrium. And as long as I don't attach stuff to this that carries the center of gravity way outside the base of support. So I put some objects on there, I start stacking metal things that wave over here and shift the center of gravity out to about that point, the thing falls over. All right, so that's the story of tricycles at rest. Why do children grow up, initially start riding tricycles instead of bicycles? It's because they're so stable. When you're not moving, they just tend to stay upright nicely. You tip them a little, they go back. They're in stable equilibrium. Well, what's the problem? Why don't we keep doing that? Well, the reason we don't keep doing that as we get older is tricycles do have a problem when they're moving. When they're going quite fast, imagine we're heading towards you. So this could be a tricycle. Suppose it was heading toward you quite fast, and now it decides to make a turn. To make a turn, it experiences static frictional forces with the ground, traction. You turn the wheel, traction forces appear at the bottom of the tricycle, where its wheels are, at the bottom of its wheels, that push it to the side so it can make the turn. But those forces act very low on the tricycle, down where the kid's feet are, where the wheels are, and they push the wheels and feet to the side. But what about the child's head and shoulders and stuff? To get the forces needed to make them turn and undergo the acceleration involved in the turn is a little tricky. The forces have to be conveyed up through the child's body from the bottom of the wheels into the body of the tricycle, into the legs of the child, into the waist of the child, all the way up. And it is quite possible, and often happens, that the child's upper body continues in a straight line at a steady speed, as in inertial, while the tricycle's bottom drives out from under the child. So you get an accident like this, where you're heading I'll have the tricycle's heading towards you, and it's going to turn, and it flips over like that. The bottom gets pushed, and the top fails to follow it. So tricycles have an instability at high speed. The body and the top part of the situation, the kid, tends to go inertial and have the tricycle drive out from underneath the kid. That's not so good. It does happen to children. It would probably happen considerably. It happened to adults doing this too. A solution is to make the base of support of the tricycle very big, so that as the tipping starts, large influences start showing up to try to return it to upright, and those help to convey the forces and torques necessary to make the person's body complete the turn. But so big clunking wide tricycles can tolerate this behavior, or ones where you've got a very low center of gravity, so it's very hard to tip you over. It's very stable. All not very realistic. What's the alternative? Get rid of the third wheel and go down to 2 wheels. And that seems like a terrible choice, but it has some remarkably valuable effects. Okay, so tricycle creates a base of support. It forms a stable equilibrium at rest. You can tip it and it spontaneously goes back. It's a minimum. When it's upright and happy, it's in the lowest available potential energy. It's a minimum of potential energy. But a tricycle is somewhat the reverse. A tricycle does not form a meaningful base of support. It touches the ground at 2 points that defines a base of support that's just a line. And if you put the center of gravity of the rider and bicycle right over that line, it's in equilibrium again. There's no net force or torque. You just barely get it. So it's the same as this. This stick forms a point base of support, which is again useless for significant stability. But if I get the center of gravity just above that base of support, I can get to zero net torque and zero net force. I can get equilibrium. You can't really do it, but you can get close. So there is still an equilibrium available, and a bicycle with rider on with or without rider actually, a bicycle can be in equilibrium. It just has to have its center of gravity dead above, perfectly above that line defined by the wheels touching the ground. But that equilibrium is not a stable one. It's an equilibrium, zero net force, zero net torque, it's, okay. But if you make excursions away from it, particularly to the sides, front and back not so much, but to the sides, you tip the bicycle left or right, it experiences forces and torques, influences basically, that push it away from the equilibrium. Instead of having an equilibrium that recovers, that experiences restoring forces and torques, the bicycle, when it's tipped to the side, experiences anti-restoring forces, forces that ruin it, that push it away from equilibrium so that it falls over. The opposite of restoring forces, in short. How does that work? Well, the bicycle, at least along that direction, is experiencing, when it's at equilibrium, it has a maximum in local total potential energy, at least side to side. When it's upright, it's a lot like this stick. This stick, as I tip it away from vertical, the center of gravity, which is about where my finger's up, right here, that's about the center of gravity. The center of gravity lowers. So this is less total potential energy than this, which is less than this, which is less than this. This is as much as I can get before I start going the other way and again lower the center of gravity. So this orientation, vertical, it's actually an equilibrium, zero net force, zero net torque, but it corresponds to a maximum in total potential energy. It's as much as I can get. If I tip the stick one way or the other, its total potential energy decreases. So this type of equilibrium, when it's up here, it's certainly not stable. It's what's described as an unstable equilibrium. It's an equilibrium that you can be in, but if you make any excursion away from it, influences appear that push you away from equilibrium and ruin it, push you away. So the equilibrium is unstable. And a bicycle is in an unstable equilibrium when it's at rest and perfectly vertical. You're just at that orientation vertical. Yep, center of gravity right over that line. It's in equilibrium, zero net force, zero net torque. In principle, it can get there and stay there. But any hint of movement away from that, and over it goes. So bicycle has an unstable equilibrium at rest. And other things that have unstable equilibrium, a pencil balanced on its point. Lots of things that are thin, a sheet of glass sitting on its edge, just right, unstable equilibrium. Don't bother it, otherwise it falls over. All right, so this explains why bicycles, when you are at rest, are very hard to keep upright. People do manage to do it. I mean, it takes considerable skill to balance, get the bicycle to stay upright. You can do it by just continuously shifting your mass around so that the center of gravity keeps moving around. You keep trying to get yourself back to the equilibrium. It's a lot like this, taking the stick, which by itself would be an unstable equilibrium, but I can sort of balance it. If I keep putting my hand underneath the center of gravity, this is the center of gravity, if I keep putting my hand under there, I can kind of keep it in the equilibrium. Okay, so people, skilled people can keep a bicycle upright at rest. But in motion, the bicycle becomes remarkably stable. And it does this for two reasons. Actually, they both have to do with steering. The bicycle steers automatically. It automatically steers its wheels underneath the overall center of gravity. So it's basically doing what I was trying to do. I'm trying to put my hand down here, this hand, underneath the center of gravity of the stick. And it's hard with a stick this short. If I take a longer stick, it should be easier. So here's a longer stick. If it goes out of screen, but the center of gravity is about here. So I want to keep putting my hand underneath that center of gravity. And now I've got some more time to work. And I can do this, I can move around and so on. You can keep it balanced. So you can fix an unstable equilibrium by continuously returning the contact point with the ground, basically the base of support that isn't big enough. You can keep returning that base of support. It might be a line, it might be a point. You keep putting it underneath the center of gravity of the stick, and you keep returning the system to equilibrium. It's an unstable equilibrium, but you can keep going back to it. And here I'm doing it by hand. You can do it balancing a broom, same idea. With the bicycle, it spontaneously steers so that that minimal base of support, the line between the front and rear wheel contact points, that line keeps going back underneath the overall center of gravity and keeps rescuing the rider and bicycle so that they don't tip over. And there are two reasons why the bicycle steers like this. Of course, it only does this if you're heading forward. If you're not moving, you lose the automatic steering process and over you go. While you're moving forward, it keeps steering under you. And those two effects are these. First, the bicycle is not a single rigid object. It at least consists of the body of the bicycle and the steering column, the front wheel, which includes the front wheel. And if you take a bicycle and tip it to the side, you'll discover that the front wheel and the steering column rotate spontaneously. And they rotate, if you turn it, if I tip the bicycle, and I actually have a bicycle, a small one that I could show you, but I don't. If you tip the bicycle to one side, the steering column pivots. And it pivots in the direction that you want to have it in order for it to rescue you if you were heading forward. Why does it pivot? Why does that front steering column pivot? It's because the overall bicycle is able to reduce its total potential energy by pivoting that way. It rotates its steering axis in order to lower its overall center of gravity. And as we've seen, objects accelerate in the direction that causes them to reduce their potential energy as quickly as possible. And so that pivoting occurs to get rid of total potential energy. It's part of the design of the bicycle. It was introduced initially by accident, and no one really thought through this. It was ultimately thought about later, more recently in the past 50 years, that people realized, oh, look at how it pivots. And if you build a bicycle that does not pivot like that, or worse, that pivots the wrong way, and it is possible but difficult to build a bicycle that does that, the bicycle becomes unrideable. You can't stay upright if it pivots the wrong way spontaneously. It then does not rescue you automatically, and you're in trouble. You can't ride it. So that's one reason the bicycle spontaneously steers under you. The fact that it can lower its center of gravity and therefore its total potential energy by steering in the rescue direction. The other has to do with the rotation of the front wheel. The front wheel has angular momentum as it rotates, and it can be described as a gyroscope. And a real gyroscope, and here's a real gyroscope. The spinning wheel in this object here is the gyroscope. Gyroscopes have weird behavior when you exert torques on them. If you exert a torque on a gyroscope, that's one of these spinning wheels, is to pivot in a non-intuitive direction. And that has to do, that's an effect known as precession. And let me try to, with words alone, try to give you an idea of why the bicycle wheel steers spontaneously if it tips and has the ground pushing up on it. So as the bicycle wheel, when the bicycle wheel is vertical, when you're just heading straight ahead and everything's great, it has angular momentum, and as the wheel turns, according to the right-hand rule, it's angular momentum exactly to your left. You know, so if I'm heading towards you, the bicycle wheel's curving like this, right-hand rule, it's leftward angular momentum. If you were riding a bicycle toward me and your wheel's coming toward me, it would be to your left. All right, so that's the angular momentum of an upright bicycle. Once you tip the bicycle, so for me, my bicycle tips so that instead of being upright, it's now topped to my left. Now, as the ground pushes up on the wheel, the bottom of the front wheel, that upward push, support force, is no longer aimed at the center of the wheel. It was when the wheel was vertical. and therefore it produces no torque on the wheel. But once you tip the wheel, it's missing the center of the wheel. That upward push is off to the side, and it exerts a torque on the wheel. And that torque, for me, is toward me. It's trying to twist the wheel this way, which is a torque toward me. So what happens then is there's a transfer of angular momentum into the wheel, because a torque exerted for time is an angular impulse. So the wheel, which used to have angular momentum to my left, now starts having angular momentum added to it toward me. And it pivots. Instead of being aimed at you guys now, it begins to pivot like this as new angular momentum is poured into it. The wheel steers. Let me try to do this from your perspective. So I may turn my back on you. So you're pedaling along, and the wheel's turning like that. So it's got angular momentum to your left, okay? But as you tip the wheel, there's now an upward push on the wheel that twists it, and the twist is that way, okay? So that twist is toward you. So the wheel precesses, its angular momentum evolved from toward your left, more and more toward you. And the wheel, which was turning like that, is now turning like this and more like this. It's steering. And that steering is also in the direction that rescues you, that picks you up, drives under your center of gravity. So those two steering effects, both combined, they work together to make sure that if you begin to tip over, you're going to get rescued. It's going to drive underneath your center of gravity and pick you up, unless you fight it, which no one in their right mind does. You can do it with your steering wheel. You can do it, make a disaster occur, but you wouldn't want to do that. Well, so far then I've got how the bicycle manages to. It has an unstable equilibrium at rest. When you're in motion, that it has a dynamic stability that shows up. It's got a natural behavior where it drives under your center of gravity and rescues you. But so, okay, still, why ride two-wheel vehicles? And the reason for that is you can solve the inertia problem that plagues a tricycle or even a car. The tricycle and car, because they have to remain upright, because they've got 3 or 4 wheels, they have a true base of support. When all their wheels are on the ground, they're upright. And it's hard not to be upright in those vehicles. When you make rapid turns in a vehicle that is forced to be upright, you tend to have the top of the vehicle, the high parts of the vehicle, or the kid on top of the tricycle, move inertially while the rest of the vehicle drives out from under them. To fix that, you need to be able to allow the vehicle to lean, to tip prior to the turn. The turn, if you think about this, let's do this so you are the kid on the tricycle. Here's the tricycle. And you're gonna turn to your left. If you do that, and all the forces are down here. So if I'm gonna push only on the bottom, you're gonna turn to the left, and that means this is down here low on the vehicle, it's gonna push you to the left. You're gonna tip over, and you're gonna tip over with your head going to the right. All right, so that's, again, here you are on the tricycle, this is your head, and the tricycle turns and you tip over, head to the right. If you could somehow lean to the left before this even happened, now, as the forces occur, they compensate. The leaning alone causes you to tip over to your left. The turning without leaning causes you to tip over to the right. You can make those two effects fight each other, so you don't tip over. And that's what you do on a bicycle. If you ride a bicycle, so unlike a tricycle, ride a bicycle, you arrange it before coming into any turn so that you're leaning the bicycle at just the right angle to compensate for the tendency of inertia to flip you over in the other direction. So just to sort of summarize that bit piece by piece carefully, if you're in a bicycle and you turn without leaning, that is, you're just going along straight upright and you just turn the handlebars to try to steer, If you steer, your body will go inertial and your head will tip over toward the outside of the turn. Okay? If, on the other hand, you lean yourself, your body, and the bicycle toward the inside of the turn, and you do that, and then you actually don't turn, you will tip over in the direction you're leaning, which is toward the inside of the turn. So, if you turn without leaning, you tip over to the outside of the turn. If you lean without turning, you tip over to the inside of the non-existent turn. If you do them both at the same time and you do them just the right amount, the two effects cancel. You go through the turn leaning, that is, you're tipped. You're not quite upright anymore. But the two competing effects, tip over to the right, tip over to the left, tip over to the outside or inside, they cancel. And you stay upright. And when the turn is over, you return truly to upright and vertical. And you're fine. And that's the beauty of a two-wheeled vehicle, whether it's a bicycle or a motorcycle or a moped. Those vehicles can lean. They don't have this natural stability of stable equilibrium at rest, and so they can tip. And when you tip them just right toward the insides of turns, you can complete the turn as fast as you like with as serious accelerations as you like. As long as they can keep their grip on the road and not skid, they can stay stable. Stable in the sense that they don't tip over. So that's what we do on bicycles and motorcycles, is we lean it into turns and therefore survive them. The same actually is true of things like a runner going around a tight bend in a track. If you try to stay upright as you run around a tight bend in the track, you'll tip over. Your body will go inertial and it will tip over toward the outside of the turn. So what do? You naturally lean toward the inside of the turn to compensate. That leaning by itself would be a problem. You would tip over if you did that at rest, but not when you're turning. While you're turning, that leaning compensates for your inertial tendency to tip over to the right, and you're fine. Right and left. You inside, outside of turn. Inertia wants to tip you over towards the outside of the turn. Leaning wants to tip you over towards the inside of the turn. Use them to compensate for one another. So that's most of the story of bicycles. We use bicycles because despite having only 2 contact points with the ground and therefore having an unstable equilibrium at rest, you can fix it when you're moving forward. The bicycles are designed to do this, and they will stay upright. In fact, children's bicycles in particular are built to be extremely stable. That automatic steering effect is quite strong in a child's bicycle, and as a result, they're relatively hard to tip over. You can tip them over, of course, but they really drive under your center of gravity nicely, and you can even let go of the handlebars, and it will rescue you despite having no hands on the handlebar. That automatic steering takes over, and so people who think they're super cool because they can ride with no hands, well, as long as everything works nicely, yeah, the bicycle is doing the steering. That's what it does. As you get to more sports-related bicycles, adult bicycles that really are nimble, can steer easily and quickly, they're not as stable. There is a trade-off between nimbleness and stability. The more stability you build into the bicycle, the less nimble it becomes. It becomes harder to steer it because it's got the automatic steering dominating. So adult bicycles, not so easy to ride, no hands. You can still do it. And so the bicycles solve the stability problem, and they allow you to lean, to tilt the bicycle. You can quibble about the word for leaning. Some physicists don't like the term to lean into a turn. In any case, you lean to the side, you tip the bicycle to the side, and going to the turn, you always tip it to the inside of the turn, and it allows the bicycle to not tip over due to torques associated with inertia and with the lean. They cancel each other. All right, and that's really enough to talk about for the story of bicycles.